look at how he does them. So that would be a sensible thing to do at this point. But I'll go through them anyway. So as always, I'm going to do that thing where I just briefly talk about all the questions, and then I'll go through some examples that are sort of similar. So anyone who's just joined us, just follow my instructions. If you click on this symbol in the top left-hand corner of your screen, you can zoom into the right-hand side of my screen. Might be a bit easier, then you can see a little bit more. All right. So question 1, I'll just start here. So part I, compute all critical points on the open domain. So we just want to find del of f being equal to the 0 vectors. You should find infinitely many points. Or, n points, to just say, oh, well, the points take the form this with an n in it, probably with a cos and sine and stuff like that. So you should get 2 cases. And what I sort of mean by that is if we have, like, either yx is equal to 0 or x minus 1, y minus 1 is equal to 0. If we need this and this to both hold, we could have y equals 0 and x equal 1, or x equals 0 and y equal 1. So that's something to consider. That's just a thing to think about. So the rest of the question is just all about marking the diagram with points as appropriate. So part 2. So as it say, on the contour diagram, mark all the critical points that are in this domain. So of all the points you calculated in part 1, just mark them all on the graph. That's so the plot here. So you have 2 images, and then there's the one on the right. Mark the critical points. Okay, and just note that in this domain, so the plot actually shows the entire domain that you're interested in. So the x being in negative pi on 2 to pi, and then y being in negative 3.4 to 3.4. So that's what's going on there. Okay, part 3. Mark any critical points along the boundaries. So any more critical points on the boundaries? Now bear in mind that if you wanted like a max and a min sort of on a boundary, it might not be a global min and max. It might be a local one for that boundary. All right, I'm going to wipe out the top half now. We'll start writing this split screen a bit differently a bit later. Now we can get rid of question 1. Part 4. If anyone has looked at Michael Bryson's solutions for the old version of the assignment, you will find something incredibly confusing written at part 4. So I was looking at this like on the weekend. Normally when I prepare my tutorial notes, I look at the solutions, look at the assignment. I'm like, oh yeah, I think I do it like that. I check the solutions and I'm like, yeah, that's how it's done. Too easy. But with part 4, I was like, where on earth did that RT come from? So don't worry about that. If you happen to look at that, don't worry about it. That's not what you don't need to worry about it. So all you need to do for this is find find the minimums and the maximums on the blue line. That's it. That's all you need to do. So don't worry about that. The question is far easier than it looks. Okay, part 5. So if the origin in the region is g of xy being less than c, so that means the inside of the blue line is g of xy being less than c, then find the global minimum and maximum inside there. So find the min and max inside the blue line, and then VI is find min and max outside blue line. So that question is a lot of it is nowhere near as hard as it looks. So don't worry too much about it. Like you literally need to mark the points on the graph. That's all you need to do. All right. So again, I encourage people to always ask questions. So there's a little chat window you can ask questions in. You can also turn your microphone on. I'm not recording the session, so ask away if you fancy that. Okay, so I'll have a look at question 2. So I'm going to write some stuff off. Start doing this properly in a sec. I should have really started with question 2. So question 2, so I've got this shape bit like that. And you have 2 dimensions. So there's a height there and a length there. So the first thing you need to do is find an equation for the area in terms of H and L. So we define our H being this, we define our L being that, so we can find the area of all this in terms of H and L. You can also find the perimeter. Find the perimeter as well in terms of H and L. So they're sort of the things you still need to do with this one to start. And then, let me actually start part 1. It annoys me. Part 1, assume the object has a fixed perimeter, then use the Lagrange multiplier technique to compute the length to height ratio that maximizes area. All right, so if we have H being, so our Lagrange multiplier, what's it? HL lambda. We want that to be the area equation minus lambda outside perimeter equation minus P, so big P for perimeter. And then we want to find del H being equal to 0. And from this we want to find a ratio between H and L. So that's what you want to end up with, is a ratio between H and L. Because we don't know what H and L are. I don't know if they're going to be 10 kilometers or 10 millimeters or 4 centimeters. We don't know exactly the scale of this, but we can get a ratio between H and L that will maximize the area. So you find this, but then we've only found, like, we don't know if this is a minimum or a maximum. It's like, is this a min or a max? And the working that is actually required to do this is just check other points. check other points sort of around. So if we get, say we get 3h is equal to 2l, so then, h is equal to 213l. I can't remember exactly what it is, but there's not that. Then it's like, all right, well, is this our maximum or is this a minimum? So I was like, all right, well, around solution. So I want to check other points around the solution. So I was like, well, what happens at h equal 1/3 L? And what happens when h is equal to L? Do we get bigger or smaller? Because if these things are bigger, then this thing is probably found as a minimum. If these things are smaller, then we've probably found a maximum here. So that's what we want to be thinking about there. And then part 2 is sort of like the reverse of what we just did. So now h L lambda is equal to the perimeter equation minus lambda area equation minus L. Sorry, sorry. What am I doing? Minus the area, and then we want to send del H being equal to the 0 vector. All right, is this minimum? So the question asks for a minimum, so it probably is, but we need to actually show that that's the case. So check other points around. Check other points around solution to see if they are bigger or smaller. That's what you need to do for that one. So it's a bit like the opposite. And if you happen to get the same solution for part 1 and 2, that doesn't mean it's wrong. I'm not saying anything. Okay. So that's question 2. Okay, looks like there's at least one other person that's joined us today. So I'm just going to tell you, if you click on a button on the top left corner that looks a bit like this, and then you zoom in, you can zoom in on the right-hand side of the screen, so you don't need to see both my screens, and you can just focus on the whiteboard, which will be a bit more interesting in a minute when I only have the assignment up on my left-hand screen at the moment. For some reason, my computer won't let me share just one screen, which is a little bit annoying. All right, question 3. Question 3, what have you got? So use the Lagrange multiply technique to find the points on the sphere that are closest to and furthest from a particular point. All right. So if we have a point being equal to 3 minus 4, 2, the distance from P to a point x, y, z, that's actually equal to distance being, let's give, sorry, just say distance is equal to x minus 3 squared plus y plus 4 squared plus z minus 2 squared. So that would be the distance between an arbitrary point and the point that we've been given. So we can just, well, d squared is just equal to, x minus 3 squared plus y plus 4 squared plus z minus 2 squared. So if you just spend a line just arguing as d increases, d squared also increases. So we just use d squared. So it's easier to use d squared because it doesn't have a horrible square root in it. And if we think about it, as the distance increases, d squared is going to get bigger. And as the distance decreases, d squared is going to get smaller. So we're just going to, you can just use d squared as long as you justify it. So I'll just quickly sort of set this out. So we have h, x, y, z, lambda. How we want to set this out is that it's d squared minus lambda outside x squared plus y squared plus z minus 1 squared minus 100. So that's sort of how we want to set it out. And obviously we can the del operator on h being equal to 0, and we should get two answers. Are they max or min? And you have a think about that. Alright, that's kind of basically how to do the assignment. Just sort of a quick and dirty. What time have we got? Got heaps of time. So I'm just going to go through a few sort of similar-ish examples. Alright, so yeah, anytime you want to ask questions, just go ahead. What did I want to look at? Then I'm going to see both my screens, so I'll be like, oh, look at all my stuff I'm doing. You'll just be able to see what I'm reading from the other screen, but never mind, eh? All right, what did I want to look at first? 2019. So in 2019, I wanted to look at question 2. So if we've got a question like this, so if we have f of xy being equal to x squared plus 2y squared, that's sort of on a circular arc. 1 minus a half squared is equal to 5 on the 4, and 2y minus x is less than or equal to 1. Use the Lagrange multiplier technique. To confirm the critical points. So this particular assignment question actually says, oh, remember you did this in an old assignment. But we will be using a different technique now. All right, 2019, where did I put it? There it is. So anyone who can see my second screen will just see that I'm about to write from this, but I wouldn't recommend doing that because I'm about to write everything from there on this screen and explain it as I do it, so you're only going to confuse yourself. All right. Might go a different color just to mix it up a little bit. So what do we have? So we have our f of x being equal to x squared plus 2y squared, and we have our g of xy being equal to x squared plus y minus a half squared. And then our c is equal to 5 on 4. So remember we have sort of a curve that's on f, and then it's like, well, what's the min and max on that particular line? Like, what's the min and max of f on the g line? Sort of what it's getting at. So what we do, we just let h of x, y, lambda be equal to f of xy. And then we subtract lambda outside g of x, y minus c. So that's just the basic Lagrange setup. And that's equal to x squared plus 2y squared minus lambda. X squared plus y minus a half squared minus 5 on 4. All right, so we've set that up, and now we just demand that del h is equal to the 0 vector. Oh, make a bit more room for the next bit. So this implies, so we want partial of h with respect to x, we want to find a partial of h with respect to y, and we want partial of h with respect to lambda. So respect to lambda is just you pretty much just take this and put a minus sign in front of it, so that one's pretty easy to work out. So we just go minus x squared plus y minus a half squared minus 5 on 4, and that's just equal to 0. And dh dy, so from the first bit we get, that's 4y, and the second bit we get minus lambda times 2y minus a half to the power of 1. We multiply the derivative of whatever's in here, but that's just 1, so that's that one done. And then for this one, it's just 2x minus lambda times 2x. All right. So now we want to solve this. So we can actually label these if we want. So we can label them like, no, that's 1, that's 2, that's 3. That can be a handy metric to use. So we multiply 1 by y minus a half. Oh, sorry, these are all equal to 0. Sorry, I should have made that a little bit clearer. So now it's just like, what's your favorite method of simultaneous equations? So we've got 2x outside, y minus a half is equal to lambda 2x, y minus a half. All right, so we've got that. So yeah, sorry, I've just moved that bit over to that side just quickly. So now we multiply 2 by x. 4yx is equal to, what is it, 2 lambda y minus a half x. Okay, so we label these things that we've just got. So we'll call that one 4, call that one 5. And what have we got? So we see that this bit here is the same as that. So so we just say that for 4 is equal to 5, so we have 4yx is equal to 2x y minus a half. So yeah, just simultaneous equations are back to haunt us again. So I hope you're good at your simultaneous equations. Where are we up to? So we end up getting, so simplify that, get to 2yx plus x is equal to 0, which implies that x outside 2y plus 1 is equal to 0, which implies that x equals 0 or y is equal to negative a half. Substitute x equals 0 into our equation 3 to get 0 squared plus y minus a half squared is equal to 5 on 4. So we just got this thing, we've subbed it into this bit here to see what we get. And then what do we get from this one? So then we get y minus a half is equal to plus or minus the square root of 5 on 2. So remember, keeping exact values, we like exact values. This implies that y is equal to a half plus or minus root 5 on 2, which is equal to a half outside 1 plus or minus the square root of 5. If you want to simplify it like that, which is nice. All right, so about to find, so we've found 2 critical points here. So call it critical point 1, so it's going to be at x equals 0 and y equals a half, sorry, I didn't shut that bracket before, a half outside 1 plus the square root of 5. And code point 2 is equal to x equals 0 and y equals a half, 1 minus the square root of 5. And solutions here actually give decimal values right at the end. 0, comma, negative 0.618. Didn't mean to write that there. Oops. All right, so that's 2 critical points. And that was just using the x equals 0. But what we haven't used yet is this y equals negative a half. So see if we can find any more critical points. Y is equal to negative a half into 3 gives us x squared plus a negative a half minus a half squared is equal to 5 on 4. So we're just subbing that right in, and that means we get x squared plus 1 is equal to 5 on 4. This implies that x squared is equal to 5 on 4 minus 1 is just a quarter, which means that x is equal to plus or minus a half. So 2 more critical points. I'll just write it like this, CP3. So we've got our x equal a half and y equal negative a half. And CP4, sorry, is equal to a half, sorry, negative a half and negative a half. All right, so we have 4 critical points. Ooh, no, it's saying there's 3 critical points. Why is that then? Why is it? Oh, there's a domain. Apparently there's a domain that exists in this question. So in this particular question, apparently there was a domain. Well, we found the critical points. There are 4 critical points. That's the end of the question. Okay, coolies. Find whatever it is I wanted to do next. So 2019, we're all done. So I also wanted to look at something from 2018. 2018, what do I want to look at? I wanted to look at something else in 2019. I'll get back to that. Yes, that one. That one actually looks a little bit similar to one in your assignment, so I thought that'd be a good one to do. Now I clicked out of 2019. That was a bit silly of me. Never mind. What do we do? Do green now. Let's try green. So not sure if I like that green very much. Never mind. Use the Lagrange multiplier technique to find the point on the unit sphere. That is furthest from the point 8 to 4. Yeah, I thought this would be a bit similar to your question 3, so that might be helpful. Well, so that's on double integrals apparently. 2018. Why did I close 2019 one? That was very silly of me. Never mind. I wasn't finished with it yet. Alright, so question 2. Just find it. Okay. So we've got this point here. All right. So we consider the point P, X, Y, Z. Okay, well, first I just want to talk about this question a little bit. So we've got the unit sphere, and we want to find the point which is furthest from this point. So this obviously isn't on the unit sphere. The numbers are way too big. Like the numbers would have to be much smaller for it to be on the unit sphere, so it's not. So we're not trying to find the closest point. We're actually trying to find the farthest point, which is interesting. So yeah, the point isn't on the sphere, and we're trying to figure out how close can we, or how far can we get from it. So we consider our point. Just get the labeling right. So we'll say Q is equal to the point 8, 2, 4. And then we're going to consider this point, which is the one which is farthest from, well, sort of an arbitrary point on the unit sphere. Consider the point on the unit sphere. Distance between P and Q can be found by D is equal to, so just normal Euclidean distance, so we've got our x minus 8 squared plus y minus 2 squared plus z minus 4 squared. I didn't need to put that close parentheses in. So this is a bit where we think about, do we really need that square root there? And we can just say, we note that d squared behaves similar to d. So this is how this question, how this set of solutions is worded. So let the function to be optimized be, so we got our f of x, y, z being equal to d squared, which is equal to x minus 8 squared plus y minus 2 squared plus z minus 4 squared. So we're trying to find the maximum value of this function. So for the constraint, we let g of x, y, z be equal to x squared plus y squared plus z squared, and c be equal to 1. So how we're setting this up is we started with this function f, which is the distance between our point Q and any other point, and we want to find the maximum. But the thing is, like, the maximum of this would be like, x is equal to infinity, y is equal to infinity, z is equal to infinity. Like, it's just going to get bigger and bigger. So now the constraint is that the solution must sit on the unit sphere. So the sphere is now the constraint bit, and the distance is the function that we're optimizing. Okay. So we let the Lagrangian function be Lagrangian function. My microphone's still working. I'll just check that quickly. Yeah, it's still working. Cool. And no one's chatting. So Lagrange function, that's going to be h of x, y, z, lambda. So it's going to be a 4 variable one this time. So that's going to be equal to f of x, y, z. minus lambda outside g of x, y, z minus c. And then we just plug everything in to figure out what that is. So we're going to get an x minus 8 squared plus y minus 2 squared plus z minus 4 squared minus lambda outside x squared plus y squared plus z squared minus 1. So we just subbed everything in. And now we find all our little derivatives and send them all to 0. So things are looking a bit too green, I think. I might change color again just to keep it a bit fresh. Maybe I'll get blue and draw a little flower here. There we go. That's a bit better. Alright, so we find dh dx. So that would mean we think about that bit, and we think about that bit. So we're going to get that's 2 outside x minus 8 minus 2 lambda x. And our partial of h with respect to y is not going to be particularly different. So we're going to get 2 outside of 1 minus 2 lambda x. And then our dh dz is equal to 2 outside z minus 4 minus 2 lambda z. All right, and then our lambda one. dh d lambda is just equal to minus x squared plus y squared plus z squared minus 1. Okay, so we want to send all these to 0. So we could just sort of I'll just be lazy. So that's our equation 1, that's our 2, that's our 3, that's our 4. All right. From 1, we get x minus 8 is equal to lambda x, which implies that so then we multiply both sides by y, sorry, and then we get xy minus 8y is equal to lambda xy. So it's multiplying everything by y, and we'll see y later. So from 2, what do we get from there? No, the question doesn't. Alright, I'm just going to follow what the question does because I can't really be bothered working this out on my own. Call me. Oh, no, that's what it's asking for. Y minus 2 is equal to lambda y, which implies that we multiply everything by x. So then we get xy minus 2x is equal to lambda xy. Now we notice that this value and this value are the same. So we just make them be equal, and then hopefully, well, it's a way to actually make them equal without having to worry about the lambda. So it sort of bypass the lambda a bit there, which is nice. So we'll label these. So we go that one a 5, call that one 6, and then we're interested in 5 minus 6. So we go 5 is equal to 6. This implies that xy minus 8y is equal to xy minus 2x. And that implies that y is equal to x on 4. Alright, so just simplify that one quickly and then call this one 7. So yeah, this is just simultaneous equations again and again and again and again and again. So just a lot of them because we've got 4 equations with 4 unknowns. And then, so we can do a bit more. So now we can see if we can, so we've used this and this. Now see if we can use this one and this one. So from 1, so now we want to multiply this by x. So what did we have? So we had before x minus 8 is equal to the lambda x, which implies if we multiply everything by z, we've got xz minus 8z is equal to lambda xz. And then from 3 now, we're going to multiply things by x. So what we did have was z minus 4 is equal to lambda z. So this implies when we multiply everything by x, so we get xz minus 4x is equal to lambda xz. And then again, we notice that this there and that there are equal. We'll label these. So what do we got? We've got an 8 there and we've got a 9 there. So then we notice that 8 and 9 are actually equal. So 8 is equal to 9. And this implies that xz minus 8z is equal to xz minus 4x. And that will give us that z is equal to x on 2. So now we have relationships between x and y and x and z. So we're going to call this equation 10. All right. So now we can hopefully find some values for x. So if we sub red, so we have 7 and 10, 4. So I'm just trying to save the color changing. 7 and 10 into, so equation 4 was this one. So we're going to sub all that in, and we're going to end up with x squared plus x on 4 squared plus x on 2 squared is equal to 1. All right. So that gives us x squared. Sorry, this implies, x squared outside 1 plus 1/16 plus 1/4 is equal to 1, which implies that when we work all that out, x turns out to be equal to plus or minus 4 on the square root of 21. Just believe me there. So we've got a few minutes left. So then, well, we've got this relation here and this relation here. So if we've got some values of x, and we can find values of y and z as well. So then we have y is equal to plus or minus 1 on root 21, and z is equal to plus or minus 2 on root 21. All right, so I've just subbed those in. So there are 2 critical points. So one thing to consider here is when we found y and z in terms of x, it wasn't like there was an x squared in there or anything. So that means when x is equal to positive 4 on root 21, it means the y and the z are also both going to be positive. So it's not that the plus or minus, you need to sort of remember how to interpret it, because if it was like, if this equation here had an x squared in it, then it's like, well, x can be this or this, but for this it can be 2 values of y, and for this it can be 2 values of y. But here each x value corresponds to 1 y value and 1 z value. So it's but it's just something to keep in mind. So plus or minus 1 on root 21, outside 4, 1, 2. So we've got, there are 2 critical points, and these are the 2 critical points. So now we need to answer the question, which one is closest and which one is farthest from the point Q? One way to think about it was the original point we had was, what was it? It was 8, 4 something, I think, wasn't it? So our original point was, oh God, where is it? Yeah, 8, 2, 4. So our Q, if you remember, was equal to 8, 2, 4. So with our two critical points, one of them is going to be the closest, one of them is going to be the farthest one. It's like, is it going to be the positive one or the negative one? And if we think about it, the positive one is probably going to be closer. Well, it will be closer. But the one where it's negative, that's where everything's negative. Like x, y, and z are all going to be negative when for the second solution. That's going to be the farthest because it needs to go on the other side of the sphere. So just this one, you only need to think about it. It didn't actually want too much in the way of which is which. So it's like there are 2 points. -1 on route 21. 4, 1, 2 is furthest from Q, and 1 over root 21, 4, 1, 2 is the closest to Q. Okay, so that's that one done. So we answered that question. And we've got a whole 3 minutes left, which isn't a whole lot of time. So if anyone has any questions, now would be a very good time to ask. But then, of course, I accept questions the whole lesson. But I don't get any questions. I'll just keep going and talking to my computer. I actually really miss face-to-face classes. I don't know about you. I'm missing them. What else did I want to look at? So I can look briefly at something. I won't be able to finish it, but I might be able to start, and you never know, that might just be useful for you. So what I'm going to do, I'm just going to drag this over. So if anyone who is focusing on this screen can now see it. So this is the 2017 assignment for this class. So we consider this function f of x, y is equal to that. And the contours represent this function, and we want to find the global minimum and maximum in the region enclosed by this line. I suppose I wanted to look at use the Lagrange multiplier technique to find any critical points on the straight line segment. So I suppose I could so we've got this straight line down here, and we want to find the minimum and maximum points on that straight line is what we want to do. So I suppose we can just sort of start to set it up, but that's probably about all the time we're going to have. So it's question 1, part 3. Yeah, the other bits of it didn't really look relevant to what you're doing, so I didn't stress about it too much. So if we have our f of x, y being equal to x outside y plus 1, and we've got our g of xy is just equal to x plus y, because that's the line. So this one here is the contour plot, and this one's just the line that's passing through it, and we want to find the minimum and maximum on that line. Lagrange multipliers are actually kind of cool. I'd forgotten about them. I haven't studied them since I was in second year, which is a very long time ago. No, I'm not that old. So we just say we let g of xy equal x plus y, and our c being equal to 0, because that was just how g was set up. I think it's just x plus y being equal to 0. Then h of x and y lambda. I'll just quickly write this out. We just want f of x, y minus lambda g of x, y minus c. Sorry. All right, and that is us. We're out of time. So, yeah, briefly discussing something is better than not doing anything at all, I suppose. Okay, well, I suppose thanks for attending. Make sure you attend other tutorial sessions. Eloise should be recording her distance one. I can't remember what day it's on, but there will be a tutorial recording. If you look at the left, no, don't do that. So look at the left-hand side of my screen now, if you like. So the left-hand side on the web conferencing thing, there's a little button here, and if you click that, you can access the recordings. So if you haven't found that yet, that's where the button is, and there's tutorials that Eloise has recorded. So just in case you haven't found that yet, that's where that is. All right. Thanks for coming along. Good luck with the assignment, and I'll see you next week.